Hello, this is an introduction to the first lab for BCHE3180, chemical reaction rates. Chemical reactions can obviously occur very slowly or very quickly depending on a number of factors, mainly the type of reactants, any intermediate steps, thermodynamics, but most importantly the concentrations of the reactants. Anyway, all of these factors are reflected in the kinetics of the reaction. Consider a general reaction where capital A and B are reactants and capital C and D are the products. The rate can then be described as the disappearance of A or B over time, or the formation of C or D over time. A reaction rate equation is then K times your concentration of A and B to some exponents, where K is your specific rate constant determined by the equation, and X and Y are the orders of each reactant. The specific reaction that we're going to be analyzing is the decomposition of peroxydisulfate in the presence of iodine solution. A secondary reaction will be occurring as well as this first reaction, where iodine reacts with the iodide ion to form triiodide. Now, the concentration of this triiodide should be pretty much identical to iodine, and because this triiodine has color, the concentration of it can be measured via spectrophotometry. Spectrophotometry measures the light transmittance or absorbance through a sample. So the absorbance of light through a sample is proportional to the concentration of any components that may absorb light. So if there are more components that absorb light, if it's harder to see through, then obviously less light will make it through the sample. This is described mathematically by Beer's law, which is shown here in the middle of the screen, where A is the absorbance measured by the machine. Epsilon is the molar extinction coefficient, which varies depending on the compound, but for us it's about 15,000 per mole centimeter. B is the path length, which is generally 1 centimeter. C is the concentration. Now, using Beer's law, we can generate the rate equation for this reaction. Now, my group member, Megan, is going to tell us a little bit more about the purpose of the experiment.
In this experiment, we're working with rate of reaction, which is really important to measure because it's a necessary design parameter for most processes. By manipulating the amount of reactants that we use, we can change the total amount of time that the process will take, which also helps us scale something from bench scale to industrial sized. In this particular experiment, we used 10 trials with different amounts of reactants, both to make sure that we get an accurate reading of the rate of reaction in the K, but also so that we can determine at what concentrations this reaction takes place and will occur in the quickest amount of time.
Wow, Megan, very insightful, thank you. Glenn, how about you pick up from here and tell us a little bit about the required materials?
For this experiment, we're going to require a couple of chemicals to prepare our solutions, as well as some equipment. To prepare solution A, we will need 0.2 molar potassium iodide, 0.1 molar potassium nitrate, and for solution B, we will need ammonium persulfate in a concentration of 0.2 molar. We will also need EDTA at 0.1 molar, as well as deionized water. For the required equipment, we will need a spectrophotometer that will be used to read the different absorbencies of our samples, cuvettes that will be used to prepare and hold our samples while taking these measurements, a stopwatch to record the time, as well as a lab notebook to record all notes, figures, and equations that are used during this experiment.
Wow, what a list. Thanks, Glenn. Hey, Connie, what exactly do we do with all these chemicals and supplies?
Prepare 0.2 molar Ki, 0.1 molar KNO3, 0.2 molar NH42S2O8, and 0.1 molar EDTA stock solutions. To a spectrophotometer cuvette, add the amounts of Ki and KNO3 specified for solution A in the appropriate table for the appropriate experiment. To the cuvette, add 1 milliliter of deionized water and 10 microliters of 0.1 molar EDTA. Then mix. Put the cuvette into the spectrophotometer sample chamber. During each experiment, configure and blank the spectrophotometer appropriately. To the cuvette, add the amount of stock solution B specified in the appropriate table for the appropriate experiment. Acquire and record data every 15 seconds for 1 minute.
Wonderful. What a fantastic sounding experiment. Well, there you have it, folks. That was the first experiment for BCHE 3180. Don't forget to like and subscribe and write a comment down below to let me know how you found this lab to be.